Okay. Well, continuing with our program, I have the pleasure of introducing Professor Michael Fernandes Gaspar. Professor Fernandes, we will talk us about Borel chromatics number of locally countable sigma graphs defined on compact spaces. Professor Fernandes earned his master's degree from the University of São Paulo, and he's currently pursuing a postdoctoral degree at the same institution. Please, Professor, you can start.
Well, first of all, thank you very much to the organizers for the invitation. And I will talk about Borel chromatic numbers of locally countable F sigma graphs that are defined on compact spaces. So I divided these into 6 sections. And okay, so why you saw some words like Borel when we're talking about F sigma graphs, and why are we considering, first of all, definable graphs? Okay, what is it? So some people called, namely Kekris, they call descriptive graph combinatorics, right? And this idea comes from this tradition of set theoretically descriptized concepts in mathematics. So for instance, the relevant sets are Borel, Lebesgue, bare measurable, and so on. So for people that are working with general topology, where you have various pathological examples, structures that, I mean, it's almost never interesting to work with metric spaces and so on. Descriptive set theory may not be so useful because it's concerned with objects that are definable somehow. So this area started with the French mathematicians Borel, and Lebesgue, and this was somehow a way to do set theory, but avoiding Cantor's paradoxes and infinites and structures that would be ill somehow. So at the time where set theory was founded, there was a huge argument between people from the school of Poincaré, the French school, for instance, that thought it was not relevant, and there was the Cantor school and Hilbert and these people. So this descriptive set theory was a way of trying to put more definability in the sets that are allowed, and avoid the usual pathologies that we find in the more abstract set theory. So for instance, those that show up in topology, in general topology. So this is a bit different from the usual general topology interest because here we are really concerned with sets that are completely metrizable, the polished spaces, and their substructures, right? And hierarchies of complexity. But we're interested in the different phenomena. So we start with a polished space, okay, and we consider a graph on it. Okay, so in particular, this polished space has cardinality at most continuum. We will say that a graph is closed if this is a closed relation when we remove the diagonal set. Similarly, we can define F sigma sets, analytic sets, Borel, graphs, Borel graphs, etc. So for instance, F sigma sets are countable union of closed sets or complements of the delta set. Analytic sets are continuous images of Borel sets, and so on. So we have, we take this approach, which is bottom up. We start with simple sets and we go on increase their complexity and see if some pathological behaviors that happen in normal topology, they still happen here, or if it's different. So generally, it's different. In the objects of our concern, they are colorings of these graphs. So for those who are used to graph theory, this is quite straightforward. So if we take a graph, okay, on a set A, and we take an ordinal, we say that we're coloring X, the vertices with alpha colors. If whenever two vertices form an edge, then they have different colors. So this should this has everything to do with the problem with the four coloring problem that says that they ask you whether you can draw any map, whether any map can be colored with at most four colors. Okay, and we know this is true. So that is the equivalently, one can ask whether any planar graph has a chromatic number at most 4. And this is true by this theorem of the four coloring problem. Okay, so here we're talking about infinite colorings, right? So we have no restriction on the ordinal. And when we have that the preimage of any color is a Borel set, so every maximally monochromatic set is also a Borel set, we say that this color is a Borel color. So this is different than the usual notion of Borel function because it requires the domain, that the codomain is a Polish space. So here we have some flexibility, but it's also it's natural to also call such a color in Borel, or you can talk about Borel partitions of your space into monochromatic sets. Okay, so how many how many colors do we need to color the graph in a Borel way? That is, what is the least cardinality of an alpha for which there exists a Borel alpha coloring of the graph? And this is called the Borel chromatic number of the graph, right? And okay, so this number can be anything from 2 to infinite or uncountable. So if we're talking about Polish spaces and Borel chromatic number, then it has to be bounded by the continuum, the cardinality of the set of vertices. And the interesting cases will be when the numbers are indeed uncountable. When we're going to ask what uncountable, right? So we'll soon shortly talk about this. So, so how can we compare these types of numbers with other types of cardinals? So here's some cardinals that are known to be in the Van Dolven's diagram. So for instance, the dominating number, which is the least cardinality of a dominating family. So it's not really relevant to know what those things are for purposes, but I'm putting here for those are failure made there. This is a cardinal invariant, a number that lies between Aleph 1 and the continuum, and the same for the following ones. So is number, which are the bound family. R is the reaping number, the cardinality of a reaping family, the least cardinality. So those are all combinatorial are relevant to set theory of the reals. H, the distributivity number, the least cardinality of a family of open dense subsets. So I'm taking these numbers and I'll put them together with some Borel chromatic numbers that are uncountable and ask if there are some ZFC provable inequalities between these numbers, right? So in my work during my doctorate, I work with a few graphs, but mainly those three. So G0, this is a graph which is a minimal graph with an uncountable Borel chromatic number. So whenever you have an analytic graph, either it has countable Borel chromatic number or its Borel chromatic numbers is at least as big as the one of G0. This graph is really, I'm not going to focus on this graph, but this is really important for this theory of descriptive graph combinatories. This is indeed very central. And there is a dichotomy related to this graph that is powerful enough to prove generalized various other descriptive set theorems, such as perfect set property or Suslin theorem. There's this graph. So this is a super graph of G0. So this gives you a hint on how G0 looks like. G1 is the set of all pairs on the Cantor space for which they differ in a unique coordinate. So we have two sequences of reals. If they're different in only one coordinate, then these form an edge of G1. And this G1 is a graph extending G0. You can imagine after removing certain edges of G1, we obtain G0. And finally, we have this relation, which is, we say that true reals, true sequences of true elements of the Cantor space, they're related if they're equal, except in a finite set, except in a finite number of coordinates. And this is the Vitalis equivalence relation. And because this really is the same relation as the one defined in the real line that says that two numbers, they are equivalent if and only if they have rational difference. This is basically the same. Here, you have to picture that in the Cantor space, the rational numbers, they're exactly, the rational numbers, the countable dense set is of those sequences that are eventually constant. So this is the same relation, basically. And what's really important is that how those models are related. Start with Aleph 1, we go to right side, okay, and we have the cardinals at Van Dolphin's diagram. And we go to the, and then we go to the left. So we can see a key number, Borel number is G1, which is related with both H and R. Okay. So for those who are familiar with these invariant of the continuum, usually, it's also that we have some diagram, and this diagram is an interesting diagram of cardinal invariant of the continuum, meaning that L0 and the finish pointing to the continuum. Okay, this will be a diagram of cardinal invariant of the continuum if we can take two of them and we can separate them. Here, this arrow means that it's less than equal. Okay, so the Borel chromatic number of G1 is less than or equal R, the repeat number. So usually we'll want to know, is it consistent that a certain part of this diagram is collapsed to Aleph 1, while the other part is the continuum, and this continuum is big, or in our case, Aleph 2. So this is the type of consistency proofs, right? So 15 minutes. And How we're going to do that? Well, we will do that more generally by looking at different classes of graphs. So, and here we have what means to be small for a graph. So let's say that, so if a graph has a perfect clique, for instance, meaning clique is a complete graph, okay, then you need at least as many colors as vertices of the clique to color your graph. Then uh, if you have a perfect clique, then it has size continue, then the Borel chromatic number is big. But when you don't have a perfect clique, then maybe you have a chance of saying that this Borel chromatic number is not so big, at least consistently. Not so big, I mean, not as big as the continue. So here we have some notions of smallness. So not having perfect cliques is one, not having four cycles is another, and we will deal in this talk with this other two, which is the one for locally countable and this notion that we invented called Allen boundedness. Okay, and we'll just state what I will just state a few of the results that I have with some other authors. So this is one with Geschke, which was my doctoral supervisor. Uh, if we have G, and G is a closed graph defined on a polished space, then either this is its Borel chromatic number is bounded by the ground model continuum, and the E0 model, which is model of one defined, then this happens if doesn't have, if the graph does not have a perfect clique. And this is bounded by the ground model continuing the silver model if the graph has no four cycles. And as a corollary, we have these two things. It is consistent with RFC that the Borel chromatic number of G1 is smaller than the one of G0, and that the G0 is smaller of G1. So we can have a picture like that. Okay, so we say that white is small, which is Aleph 1, and black is big, which is Aleph 2. So we have a picture that is exactly like that. So these are two different models signing two different values for these cardinals, okay? They follow because, of course, this the graphs G1 and G0, they fall into the category of closed graphs without perfect cliques. G0 has no four cycles. And we know that these models, when we force with, I mean, in this E0 model, the Borel chromatic number of E0 is big, and in the silver model, the Borel chromatic number of G1. Okay, you don't really need to understand this part. I just wanted to mention a few results that go in this direction, but the one I'm going to talk to you is this. This is with Banerjee, and this is a doctoral student in University of Hamburg. And it says, if we have a graph which is as complex as F sigma, so union of closed graphs, and this has a closed cover C, defined on a totally, this closed cover is count, defined on a compact, totally disconnected polished space X. Then its Borel chromatic number is bounded by the ground model continuing the Miller model. If this graph is locally countable, so this is as small as locally countable, it has Borel chromatic number bounded by the continuum. In the Lever model, if the graph is LC unbounded, which is a notion that we will define. And in particular, we will follow that the consistency between D and B. So in principle, it was more interesting to handle and separate these Borel between Borel chromatic numbers, but the question B here that asked about the Borel chromatic number of a zero in the labor model was an old question. So we decided to tackle this problem as well. And I will explain this application at the end. Particularly, we have this type of model. Something happens in the Miller model, and something different happens in the labor model. So in the labor model, B is big, and in the Miller model, D is big. So here should be Y. Actually, there is a typo where R was. Okay, so here we have just recalling the definition of a locally countable graph that says that every vertex has at most countably many neighbors. And here we're going to define a different notion of graph. So we have this graph, and this is F sigma. It has these closed covers of the graph. So their union equals the graph. So we define a G locator for this function. Okay, this is some type of rank function, but I'm not going to be calling rank function, but rather a locator, which is going to decide whether it's not in the graph, whether it's the identity, or if this is in the graph, where exactly is it? Okay, so one thing that I forgot to mention is that we can assume that this closed cover is a chain, is increasing. So we have this function that says we take X and Y. If they're equal, then we set up this to 0. If they are not neither in the graph nor equal, then they are infinite. If we have that they are in the graph, then we try to find the least number, the least CN in which they are. Okay. And we say that the graph is unbounded, and there comes this new definition. If whenever we have an edge of the graph, and let's say that this edge has location N, then we can have an open set around X such that everybody around, everybody except for X in this neighborhood has bigger location, has larger locations located further. So here's one picture of how these would be. So we have Y and X, they're connected, and all of those Z, they are outside of this neighborhood around. All of the Z in this neighborhood, they're not X, they have to be above. Okay, as it's written in there. They have to have bigger location, farther location. So obviously, the main example that we have here, which is the graph, the Vitali relation, is an example of FC. There is this graph of convergent distance, which is, we say that two reals they form an edge if they have distance an epsilon n, which is a sequence of positive real numbers. And this also has uncountable Borel chromatic number. Okay, 125 minutes. Okay, so I think I'll speed up a bit. So we have a tree. We will define a Miller tree. So basically, a Miller tree is something that is a tree that such that every node has an extension that splits infinitely many times. The Miller forcing with the node by this M. And the difference of that from Lever tree is that in a lever tree, when it splits infinitely many times, it splits infinitely many times above this part. So here I have a picture. So on the left, we have a Miller tree. So we can see that we can extend the stem. So we can prune. This is one way of pruning. You know, we just need to ensure that eventually you have infinitely many successors. And here on the right side, we have a lever tree, and we have this restriction that we cannot everywhere increase the stem. Once we have the stem, we can prune, but we need to leave infinitely many successors everywhere. Okay, these are three on the left is related to the dominating number, and on the right to the bounding number. Here we have some set. Let me just go quickly through some stuff. So this is the set of branches through P. This star 0P is the natural order preserving injection that maps these elements of omega to the less omega to the splitting node. So if you look at any of those trees, we have a very natural injection from omega to the less omega into that tree. That's what we're taking. Okay, this is the definition. You don't need the definition, you just need to have some intuitive picture. This is just because I want to use parameters omega to the less than omega. Here we extend this to the elements of the Baire space, okay, this function. Here restriction of on a node of sigma or p. Well, the diagonal here, this is the diagonal level. I think there are 13 definitions, so maybe this one is important. So what is a frontier? Okay, so here I'm just trying to put some elements that will be important to work out the proof. So we say that this is a frontier. A is a P frontier if and only if whenever we take an element of P, there is a unique real and N such that this happens. Okay, so X. So this is saying that it intersects this frontier in a unique, every real intersects the frontier in a unique N. And here we have the notion of chain of frontiers. Okay, so when we have something in an plus one, there is a unique tau in the previous part of the sequence that is a proper extension, and that's it. This is a chain. Okay. 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 I think due to the time, I'll just explain that this is some kind of setup that we need to work with the frontiers later. This is a different operation now. So the operation star 0 is going to work for the Miller. It's going to be suitable to handle the Miller case. The operation star 1 is used for the Lever case, and this has to do with frontiers, etc. Okay. Okay, then similarly to the star 0, we do the same here, define the diagonal. This map is an auxiliary map that is doing some transformation also to help us walk on the frontier. But okay, so you have all the slides. I'm not getting into these details, but I will explain what's the point of it all, right? The point is that we have one fusion that works for Miller, one type of fusion argument. And we have another fusion that is more suitable for lever to work at least with this problem. And this fusion takes into account when we can define frontiers. Okay. And in the end, what we have is that if we have some kind of transformation that it preserves height order is an injection, we have a condition of the lever forcing a B chain, then we can do some procedure like this to get a stem preserved in lever sub-3. Okay, so what we're going to do is to get a more suitable one. Okay, now we do the part that's related to forcing. We suppose we have a name for an element of 2 to the omega, and this is going to be our universal compact space. We're going to use that as Polish compact space, totally disconnected and so on. So we have the following property. Okay, whenever we take some node, we can find a ground model real that approximates, that it is forced to approximate this real that's added by forcing by this ground model real up to some point. So when, in a way that if you take sigma and you take k successor, then this decides that your real equals to this ground model real up to the cardinality of sigma plus k. Okay, so this decides more and more of your real. So we're using this technology to talk about reals. And using that, we can define some ground model function like that from the condition to the reals. It's explicitly defined like that, such that this maps the generic real to the real number. The generic real, for those who know forcing, is the unique real added by this type of forcing. Can be Miller or it can be Lever in this case, but this gives a continuous function that reads the name continuously. Gives a function that reads the name continuously. Okay, this is called continuous reading of names. And then we have this simple observation that if this is ground model, then this has to be one of the guiding reals. Or, and this is the interesting case, and that's why we introduced frontiers, we can define a notion of P rank on this, okay? And the notion of P rank is defined like that. We say that the rank of a node is 0 if for infinitely many natural numbers, the guiding real of this node is different than those of their successor for infinitely many. Okay, this is 0. But when this is not 0, this is bigger than 0, but finite, well, then it means that this is not less than k, and this gives some recursive definition. So we get to 0. So basically we have, okay, either there is one for which the rank is undefined, and this is x, then is a ground model real or not. Okay. In the case which is not, let me just see one thing. Where is this picture? Yes. Okay. So, okay. When this is not a ground model real, then we can find this stronger condition in our chain. All of these, everybody in the frontiers have rank 0. We find initial segments of the guiding reals for these guys such that the following happens. So these initial segments are disjoint when they are in the same frontier. These ensures that this condition decides up to sigma 0. Here, some compatibility condition, but more importantly is this one, okay, that says that for in situations like that, okay, we can start with somebody that has a big rank and go up so that we end up with somebody having rank 0. And using these items, okay, one can prove that the function is also injective. So we have a function that reads names continuously and injective. This is a result from Gray, but the only place where I can find this is this paper from Brendel, Yuri Komsky, and Vohovsky. So you can find it there in the proof. We just use this idea as a starting point, because we're going to do something more complicated. And here we are illustrated how these frontiers are working. So we have a Miller tree. We are not sure that we have different. So in a yellow part here, we look if there are infinitely many successors with different guide rules of a node. We don't know, but this is a finite step away from somebody red in here. Okay, so these are different tiers. They can have a very weird form. It's generally increasing. Okay, so these kind of rank arguments are actually quite standard for labor force. Okay, but once you studied labor force, okay, how much time do I have? Okay, okay, so we assume we already have a condition like we want. We again we will do the lemma now, talking about only the single case and not iterated labor or Miller forcing. So here we have an F sigma graph defined on our compact space. It has a countable closed cover C. So we define a stem preserving extension such that the set is independent. Independent, I forgot to say, but in graph, this is standard, which the independent, I mean, is monochromatic, meaning that two elements on it do not form an edge. When that happens, we can assign unique color for this set. And also note that this F is injective, so this is the injective image of a compact set, continuous image. This is not compact of a closed set. This gives a Borel set. It could be not the case because it's not compact, but since this is injective, we indeed get Borel. So for the Miller forcing happens when G is locally countable, and for the labor forcing happens when G is LC bounded. Okay, so I'll try to talk about this in 6 minutes and see if I have or less than that. So basically, the idea here is to construct something like that, okay? Looking at different sigma taus, we will say that the distance between these two open sets that are related to the guide embryos, they are some function of the cardinalities of these nodes. So if they're incompatible, then we sum them two and remove 2 times their difference. So basically, we are controlling the locator using the cardinality of those parameters. So this works more or less like that. So the one side, we have the condition. The other side, we have the guide embryos. And so if we look at I have sigma prime, I have sigma. This one has height 1, and the other one has a height 2. So we sum them, so the location has to be at least 3. That's how we do these combinatorics, okay? This is probably just one way of doing that, okay? But we thought this was more clear and elegant. Once this is done, okay, we get our Miller tree. And here we prove that, in fact, after we end up, basically, we end up avoiding everyone, and the distance gets infinite for the images, for the image of the function. So the set, so we don't have edges of the graph in the image of the function. Does not, its square does not, the graph of the function does not intersect the real graph. Okay, I'm speeding up a little bit because I just saw I have 9 minutes, and I do have some preprint, and the proof is quite complicated. So, but basically we do that by induction, not only on the dimension, but also we use the lexicographic order to walk on these trees. Okay. So, and yeah, and then we have some induction hypothesis, and at some point we need to use local countability to increase our induction hypothesis, to do our induction steps and use the closedness of all these of this cover to get the open sets. The labor case is similar, but then there are some changes that needed to be made because we use a different star operation for the labor. But then here the proof kind of parallels. Okay, there are ideas that are similar, but instead of using local countability at a point, we use L-boundedness at a certain point. Okay, so here we use LCM boundedness. Okay, so we obtain something similar to the Miller case, but we need a different hypothesis, just because of the different nature of the between different natures of Miller and labor force. Okay, so let me just jump to the these proves only the single part. I should really talk about what happens when we are talking about iterated forcing. Okay, now we need to extend this result for iterations. But I really never talk about this in public because it's already quite complicated to explain a single case. So it would take probably another hour to really explain the iteration, you know, and there are various details and a nightmare notation. So here I'm just showing you some of the elements that show up. Okay, so we need to work with tails, and there is of course force inside of forcing. We need to generalize the notion of guiding reel that worked for the single case. We need to generalize for iterations in a suitable manner. We need some notion of faithfulness, but now for iterations that is similar to those conditions that we had before in the single case that use parameters in the sigmas. And in the end, we do some fusion. Okay, we can construct some fusion for the iterated labor forcing and get this function defined explicitly like that after everything we did. which will be a continuous injection, mapping the generic sequence to the new real, and also will give us an independent set, so monochromatic set. So this is fairly complicated. I was quite optimistic, thinking I'll have time to talk about everything. Let me just put this application here. So this notion of measurability here, I hope if you read, you are convinced that this is similar maybe to the Lebesgue measurability or Bayer measurability and so on. And we have, since these notions, they are intrinsically related to forcing, we also have a notion of measurability for various forcings that that are interesting, okay, and they are different from Bayer category, Lebesgue measurability, among others. And one of them was asked. Okay, there was a question here that asked this corollary, whether it happens that every sigma 1, 2 subset of the Bayer space is labor measurable, but there is a delta 1, 2 subset of the Cantor space which is not vitally measurable. The original question was about silver, but I decided to talk about vitally, which is stronger. And then we responded to that question. Yeah. Okay, so here are some of the bibliography. They are in the preprint form still. Hopefully they should appear soon. And thank you so much. Gracias. That's my talk. And I'm really sorry that, I had to rush at the end. I really underestimated some of these concepts, how hard they are to explain.
Thank you very much. Is there a question for Professor Michael?
No.
Questions?
I can actually ask a question for everyone because when there is this definition of unboundedness and local countability. So we talk about unboundedness and the other side, local countability. We know that everything that's unbounded is locally countable, but we don't know whether there is some locally countable web sigma graph which is not unbounded. So this is a question that some of you can think that I always ask topologists that could come up with weird examples, Anyway, and
Very interesting. If not more questions, we present the certificate of Professor Michael. Professor, thank you very much for your participation in this third International Congress on Topology and related topics. Again, thank you.
Thank you for the invitation. Hey.